Hello, good evening, my dear friends. Welcome back, all of you, to the channel of learning. We'll continue with today exercise 9.3, where we stopped. I think last time we finished up to question number 12. So I believe you have practiced it once again. Please do make sure that after the classes are over, you do practice. So we'll try to solve up to question number 24, today's class. We don't know how long it will take, but we'll try to do at least up to question number 24 today, at least. So yes, I think it's time to get ready. I believe all of you have your pen, paper, book. Good evening, Neil. Nilamoto. So I believe all of you have your book, pen, paper, everything ready with you. So yeah, I think it's time to begin then. So alright then, so let's continue with question number 13 from where we left in that last class. So last class we finished up to question number 12. So today we will continue with 13. So I believe you have those formula sheets, whatever you have written, all in front of you. I believe everything is in front of you at the table. Please do see to it that it's done like that. So that learning will be fun and it will be easy also. Alright, let's continue with question number 13 then, shall we? How many terms of a geometric progression, as it is given here in the question, 3, 3 square, 3 cube, how many terms of the geometric progression are needed to give the sum of 120? So how many terms would be required to give the sum as 120? We do not know. So yes, we will assume that let n terms of this geometry progression combine together and give us the sum 120. Now for that, let's get the first term. So here the first term 3. Common ratio divided into terms. So, alright, 9 by 3, fine, that's going to be 3. So, of course, this is greater than 1. And then, of course, we will assume let n, let sum of n terms, let sum of n terms be 120. So, then it will imply Sn is equal to 120. So sum of n terms, since the value of common ratio r is greater than 1, we will be using the formula a into greater than 1. So r comes ahead, divided by r minus 1 should be equal to 120. So let's substitute the respective values and calculate. Chalo, let us do. So that will be a value is 3, r 3 power n minus 1 divided by 3 minus 1 is equal to 120. So 3 power n minus 1, I'll just directly cross multiply, that is 120 into 3 minus 1 is 2. You cross multiply 2, this comes 3 down, so 340. So 3 power n minus 1 is equal to 80. So 3 power n is equal to 80 minus 1, that goes to the other side, that becomes plus 1, so 80 plus 1, 81. So 3 3s are 9, 9 3s are 27, 27 3s are 81. So 3 power 4 is 81. I think you're done. I'll just write here. So that will be 3 power n is equal to 3 power 4. That implies n is equal to 4. That means sum of 4 terms will give us the sum 120. We can check that for ourselves. Sum of 4 terms means first, second, third. So next is going to be 3 power 4. So these 4 terms combined will give us 120. We can do a quick check on that. That is 3 is 3. 3 square is 9. 3 cube is 27. 3 power 4 is just now we have seen 81. So it's 9, 10, 17, 20. 2 left, 8, 9, 10. You can see exactly 120. So that is the application of this formula, Sn, sum of n terms of a GP. That's why we use this. Quickly we can calculate. Alright, we can move on to the next question, that is question number 14. Let's have a look at the next question, that is question number 14. Okay, the sum of the first three terms of a geometric progression is 16 and the sum of the next three terms is 128. Determine the first term, the common ratio, and the sum to n terms of the GP. What does the question say? The sum of the first three terms. Okay, we will just assume let A be the first term and R be its common ratio. Alright, so that being assumed, let A be the first term and R be the common ratio. I'll not write that, you can write it down. Now as per the question, it states the sum of the first three terms. Okay, as per the first case, it states sum of the first three terms is 16. Let's see what we can have from here. Sum of the first three terms is 16. So let's see what we can have from here. So first term, of course, A. This, I believe, now we are getting used to the geometric progression. So next step onwards, maybe from next problem onwards, we're just going to write directly and all. So A, that is AR plus AR square is equal to 16. So that will be A, just common. We might need this condition, R square is equal to 16. Let's keep it as it is because we cannot proceed any further from here. So most probably the second condition, I guess, will help us out. Second case again, it states, alright, the sum of the first three terms is 16, done, fine. The sum of the next three terms is 128. So first, second, third. So next three terms is first, second, third, fourth, fifth, sixth. So fourth term plus fifth term plus sixth term. First, second, third, fourth, fifth, sixth. The sum of the next three terms is 128. 128. Let's see what we can have from here. So now, all right, AR, fourth term will be A into R, 4 power minus 1. So that's going to be like R power 4 minus 1, 3. AR 4 power 4 plus AR power 5 is equal to 128. So maybe here, what we can do, we can take AR cube common. What will we have then? If we take AR cube common, 1 R square, 128. You can see some interlinking between these two problems. That's why I marked it as equation 1. We might use this because A into 1 plus R square can be written as 16. Is A into this value can be simply written as or substituted as 16. So, and that will be 16 R cube will be equal to 128. Let's say from 1. So R cube will be 128 by 16. So 16 in here, I guess 16, 8. Okay, 16, 8, 8, 6 are 48, 4, 11, 1, so yes, 16, 8s are 128. So R cube is 8. So R will be cube root of 8. So the value of R is 2. So the value of the common ratio here is 2. So what are we supposed to do here in this question? We are supposed to find the first term, common ratio. So okay, we have got the common ratio. Now we can go and solve and get the first term. So R, we can substitute it in any one of the equation. Alright, we'll substitute it in equation 1. So let's say from 1, A, 1 plus, R value is 2. 2 square is equal to 16. So A into 2 square, 4, 5, 6, 7 is equal to 16. So A value, the first term is 16 by 7. You should not be expecting perfect values, okay? These are normal values. You should not be expecting every time like good natural numbers, 4, 6, 10. No. These values are very common because up to class 10 standard, especially our in our NBSE board, we are used to almost perfect values like 5, 6, good numbers what to look to watch also. No, these numbers are also normal. So please don't panic when you get I got a equal to 16/7, so something must be wrong. Absolutely not. As long as you're doing, you should have that confidence. Okay, mathematics is always done with confidence. You should always have that confidence. Alright, then the next question is find the sum to n terms of the GP. So here R value is of course greater than 1. So then let's find out the sum to n terms of the GP. I'll write down the formula once again. A into R is greater than 1. So R power n minus 1 divided by R minus 1. So A value 16/7 into R value is 2 minus 1. R is 2 power n minus 1. So that's going to be 16/7, 2 power n minus 1. Because 2 minus 1 is 1. So that's done. Job done. Chalo, let's go to 15. I guess you're done. Okay, let's go to question number 15. Another simple question. Given a geometric progression with A, generally the first term, with A 729, okay. Seventh term 64, determine S7, sum of n terms up to 7 terms. So we need of course common ratio. These conditions will help us get our common ratio. Let's see how it will help us. Let R be the common ratio. Okay, so we'll assume the normal R to be our common ratio. So also given that is seventh term is given to be 64. So that's A R power 6 is equal to 64. Now the value of A is 729 into R power 6 is 64. So R power 6 is 64 upon 729. Now let's see what we can do from here. 64, that's 2 power 6, isn't it? 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32, 32 2s are 64. And 729, I guess 81, 2 2s are 3 3s are 9, 9 3s are 27, 27 3s are 81, 81 3s are 243, 3s are 729. Alright then. So in that case, R power 6 is 64 is 2 power 6. 729 is 3 power 6, so we can have this common exponent. So then that implies R is equal to 2 by 3. 2 by 3 of course is less than 1. Its fraction is less than 1. Fine then. So we have our value of R, so we're supposed to find out S7, no problem at all. Then S7 will be A into, once again I'll write down, R is less than 1, so R power n, 1 minus R power n, 1 minus R. So that value will be A value, what did we get? 729. 1 minus R value is 2 by 3 whole power n. So maybe I'll use the second bracket here. All divided by 1 minus 2 by 3. Let's simplify and solve. 729 okay, sorry, this is also 7. So just now we're at 64. 64 into 2, 2 4 are 8, 2 6, 128. So 1 minus 128 divided by, and this was 729 if you remember. 729 into 3, 3 9 are 27, 2 are 2 are 6, 7, 8, 3 7 are 21. 2187. I think we will need to do a little bit of simplification here. So that's like 3 minus 2 by 3. I'll be doing all the steps. Please bear with me. Those who can, you can just do. 729. This is the LCM. 2187. 2187 minus 128 upon 1 by 3. So that's going to be 729, 3 comes numerator into 3 into 2187. 2187, 128, so that's 9, 2, 3, 4, 5, 6, 7, 5, 502, so that's like 2059, 2187. If you remember 2187, we had calculated 729 into 3, so done. So the value is 2059. But this is the sum of seven terms of the given geometric progression. All right. Okay, let's move on to the next question then. I believe this is done. So the next question again would be question number 16. Question number 16. Find a GP for which sum of the first two terms is minus 4 and the fifth term is 4 times the third term. You can go case wise, okay, condition wise. Find a GP for which sum of the first two terms is minus 4. Let's have a look. Let's focus on the first condition only, and then we can go to the second condition and try to combine or interlink those two conditions given to us. Alright, then once again, find a GP. Question number 16. Find a geometric progression. Find a geometric progression for which sum of the first two terms. Sum of first two terms is minus 4. Sum of the first two terms means A1 plus A2 is minus 4. So A1 generally is first term A. A2, that's the second term, AR. So that's minus 4. Always do remember, okay, I'll give you an example like this. When you want to, generally when we write geometric progressions in general, no, in a sequence, you can always assume AR square, AR cube, AR power 4, I will go on. This is the first, second, third, fourth, fifth. The sequence continues, the progression continues. Alright, I had given you some important note, like when sum of three numbers are given in GP and whose product is given, that is separate case, another case, okay? So here also we can have A1 plus R equal to minus 4. Maybe we might need this condition. So let it be, because we cannot simplify it further again. Second case tells us what? Fifth term. The fifth term is equal to 4 times the third term. 4 times the third term, no problem. That is AR power 5 minus 1. 4 is equal to 4 into AR square. No? 3 minus 1, 2. So, alright. Fifth term is 4 times the third term. Alright, let's continue. The fifth term is equal to 4 times the third term. So find a GP for which sum of the first two terms is minus 4 and the fifth term is 4 times the third term. Let's simplify. You can try. So I'm just rubbing this off. Alright, so that might give me AR4 AR square 4 times. So R square is 4. That means R is equal to plus or minus 2. Remember, no? As I told you, square root, square, R square. If you have 4, then R is a common ratio, so it can be negative, it can be positive also. So we will be using plus or minus 2, because plus 2 square is also 4, minus 2 square is also 4. Alright, so you have the value of R as plus or minus 2. Now, to take both the cases of either plus or minus 2 for the value of R. So, for R is equal to plus 2, what will be the value of A? A into 1 plus 2 will be equal to minus 4, so that is A into 3 equal to minus 4. In that case, A will be equal to minus 4 by 3 when the common ratio is plus 2. So in that case, our question was find a GP. Alright, so let's get the GP. So in that case, the geometric progression is A. First term, okay, AR square dot dot dot. So in that case, A minus 4 by 3. AR, that is minus 4 by 3 in the common ratio 2 minus 4 by 3 into 2 square dot dot dot. 3 terms are enough. So that's minus 4 by 3 minus 8 by 3. 2 square is 4. So minus 16 by 3 dot dot dot. So when the common ratio value is plus 2, then in that case our required arithmetic progression will be minus 4 by 3, minus 8 by 3, minus 16 by 3, and so on. And so on. Alright, okay, that's the first case. Second case is when R is equal to minus 2. This is the second case now. When the value of R is equal to minus 2, then in that case, this will be minus 1 minus 2 as per the equation 1. Okay, let's say from 1. So in that case, we will have minus A equal to minus 4. So in that case, A equal to 4. In that case, A is equal to 4. Alright, so in that case, the required GP will be almost similar. So A is 4. 4 into R is minus 2, 4 into minus 2 square dot dot dot. So that will be 4 minus 4 to are 8 minus 8 comma 2 square 4 4 4 16 dot dot dot. So this will be the required geometric progression when the value of R is minus 2. So we have two conditions. Once when the common ratio is plus 2, once second when the common ratio is minus 2. So for both the cases, we have two geometric progressions working out. Alright? Okay, fine then. Let's go to the next question, that is 17. Question number 17. Done? I'll rub it off. Okay? Alright. You can prepare yourself with question number 17. 17 states, if the 4th, 10th and 16th terms of a GP are x, y, z, prove that x, y, z are in GP. Okay, let's see what is given first. After that we will discuss. But of course, yes, let us just discuss them. If 4th, 10th and 16th terms of a geometric progression are x, y and z, you have to prove that x, y, z are in GP. We have to prove that x, y, z are in GP. What is x, y, z? That's already given to us in the question. That is 4th term is x, 10th term is y, and 16th term is z. With the help of that, with the help of this little knowledge, you have to prove that x, y, z are in GP. See, if 3 terms are in GP, one thing that we know for sure is like their common ratio will be same. Y by x is equal to z by y. Maybe we can just take the help of this simple concept and prove that they are in GP. Alright, let's see whether we can or not. Definitely we can. You know, if we try, we can. There is always a solution. So let A be the first term. You can write, let A be the first term and R be the common ratio. Let A be the first term and R be the common ratio. Alright, then let's see what we can have. Given first case, fourth term is x. So that is AR cubed. No, 4 minus 1, 3 is x. Fine. Also, another term that is given is 10th term is 16. 10th term is 16. That is A10 is, 10th term is y, not 16. 10th term is y. So that is AR power 9 is equal to y. Equation 2. Fine. And the 16th term is z. So that's AR power 15 is equal to z. Okay, this is what we have. There are many ways, 2-3 ways to prove that it is in GP. To prove x, y, z are in geometric progression. That is, you can use the concept of geometric mean also, or if you don't want to go up to that geometric mean concept, you can keep it very simple, because if 3 terms are in GP, it means that they have a common ratio between them, among them. So now let's see. Now let's try to keep things simple. Now let's see what we have. Y by x, y by x, y by x. AR power 9 divided by AR cubed. A R power 9 minus 3, that's R power 6. Z by y, AR power 15, AR power 9, A R power 15 minus 9, so that's also in R power 6. So as we can see that we have a common ratio here with respect to this question, that is both of the cases we are getting R power 6, R power 6. Y by x is equal to z by y. That also will verify the geometric mean concept only again. Because as the concept says, if the 3 terms are in GP, then y by x, the concept of geometric mean comes from there only. Then in that case, y square should be equal to x into z. We'll get that same proof here only. But either way, it's all the same. So since y by x is equal to z by y, it implies x, y, z are in geometric progression. You can do it in many ways. Let's keep things simple. The lesser the formulas to remember for us, the better for us. More presence of mind, I believe, is more important. Presence of mind, I believe, is more important. No, question number 17, it's not like that actually, because 17 is like, as they say, no, 4th, 10th terms, 4th, 10th and 16th terms of a different GP are x, y and z. And then we are to prove that this x, y, z also are in GP, geometric progression, individually again, like respectively, it's separate, not of the same progression. Okay, so these terms happen to be in geometric progression. That's what the question says. Okay, Hilal? So don't be confused. It's not about that same. It's not like as you mentioned that, okay, 3 terms of a GP prove that they are in GP. No, it's not like that. I mean, if I've got you correctly, I hope I've got you correctly there. So there are 3 terms of a given GP. 3 terms, that's the 4th, the 10th and the 16th terms they observe are in of a GP are x, y and z, and coincidentally what happens is this x, y and z also happen to be in geometric progression, and we are supposed to just prove that. So that's the concept behind the question. Okay, I hope that's fine, Hilal. All right, thank you. No, you do not need to be sorry, of course, you're just clarifying your doubts. Why do you need to be sorry? Actually, I'm very happy that you're trying to communicate, so it's good. It keeps me active also, so I appreciate that. Okay, I really appreciate that. Why should you be sorry? You're just clarifying your doubts, genuine doubts, and I'm very happy that I have genuine viewers here with me. So it really feels like I'm teaching in the classroom. So that atmosphere, that feel is there, where students are watching, genuine watchers, as I state again. So you should not be sorry at all for clarifying your doubts. Absolutely not. Okay, let's go to question number 18 next. Find the sum to n terms of the sequence 8, 88, 888, 8888, and so on. Okay, this is a rather interesting question. Let's see how we solve this particular question. You have similar questions with this. Sometimes this 8, 888, this is changed by 7, 77, 777, sometimes by 1, 11. Same concept, same theme, same idea to solve. Okay, this particular question. Sometimes 4, 44, 444. So these are like some like common questions, common but unique questions. All right, let's see. The question is, find the sum to n terms of the given sequence. So you're supposed to find out the sum to n terms of the given sequence. That's 8 plus, so it becomes a series. 8 plus 8, 8, 8 plus n terms. So you're supposed to do that up to n terms. Now, let's begin. For all the questions, for all this common type of questions, you will do it in the same way. So maybe what you can do is you can, after this exercise is done, after this video, you can try to change it to 7, 777, 777 or 444 and try it again. You will understand whether you've got the feel or not, whether you've got the concept or not. Okay. So in this case, what I'll do is, I'll take 8 common from each of these terms. So that will be left with 1, 11, 111, 1111 plus n terms. That's the first step. To find out the sum to n terms. So since this at the current moment is not in geometric progression, so we cannot simply add its terms because it will be 11, 111, so this is not in a geometric progression. So we'll try and convert this into either geometric progression or maybe sometimes in arithmetic progression and find its sum. So that is what we will be doing. Then, again, it's still not in GP or in AP. So we will multiply and divide by 9. That is, we'll multiply by 9 in each of these terms. So we will have to divide by 9 also, common terms. So 9, 99, 999, 9999. 3 terms actually are enough up to n terms. Now why are we doing this? Some of you may be wondering, why are we just multiplying and adding by 9 and on? As I say, this is still not in geometric progression or in arithmetic progression or a harmonic progression, whatever progression be, it's still not it is still not a progression. So we just cannot add or find the sum to n terms. So we are just trying to convert it either in geometric progression or in arithmetic progression or any kind of a progression. So that we can get the sum, use a theorem provided to us, and find the sum to n terms. Still not done yet. Still it is not ready because, but now this step that we are going to do now will change everything. The whole complexion of the problem, that is 8 by 9. You see, 9. This, is it okay if I write as 10 minus 1? You will see the wondering the next 2-3 steps, okay, what we are trying to do here. I guess that's fine, no problem. I guess 9 I can write it as 10 minus 1. 99 I can write it as 100 minus 1. No problem with that. 99 I can write it as 100 minus 1. So 100 minus 1. 100 means 10 square. Fine. 999, 1000 minus 1. So 1000 means 10 cube. 10 cube minus 1 plus, let's not write down this one. Up to n terms. I guess you're slowly getting the feel there, what we're trying to do here. Now, 8 by 9, let's group them together. This 10 terms, 10 power terms, let's group them together. This 1, let's group them together. Let's separate them. Okay, let's separate them. So 10, plus 10 square, plus 10 cube, plus 10 power 4 will go up to n terms. And this minus 1, minus 1, minus 1, minus 1, minus 1, up to n terms. Now, by taking a minus common, it will all become plus. I think that's fine. There's no problem so far. Okay. Now with this, what changes is, you see, now you tell me, hasn't this become terms of a geometric progression? Tell me. 10 means 10 power 1. So if we just take this out separately, like 10 square, 10 cube, don't these terms represent the terms of the geometric progression? It does, doesn't it? It does represent terms of a geometric progression. So that's what we have been trying to do here, up to n terms. So here, what is the first term that we have? It is 10. What is the common ratio? That's like, okay, 10 squared by 10. So that's like 10 that is greater than 1. So we're going to use the sum of n terms of a GB where value of common ratio is greater than 1. So that will be a r power n minus 1 divided by r minus 1. So we will be using that particular concept. So then this becomes a. What is the first term here? 10. Sum, that's why we are adding sum to n terms. R, what is the value of r? 10. Power n minus 1 divided by 10 minus 1. Minus, what is this value? 1, 1, 1, 1, you add up to n terms. What will you get? Okay, for example, like, if you add 1 10 times, 1 plus 1 plus 1, or 5 times, what do you get? What do you get? 1, 2, 3, 4, 5. You get what? 5. You add 1 10 times, what will you get? 1 plus 1 plus 1 plus 1 plus up to 10 times. What do you get? 10. So likewise, 1 if you add n times, n terms, 1 plus 1 plus 1 plus 1 plus n times, what will you get? Exactly so. You will get n. Simple as that, no? 1 you add 5 times, you get 5. 1 you add 10 times, you get 10. So 1 you add n times, what will you get? N. Almost done. Almost done. So this will be 8 by 9 into, I'll just multiply now. So that's like 10 into 10 power n minus 1 divided by 9 minus this one, 8 into n by 9. So that will be 80 by 81, 10 to the power n minus 1 minus 8 into n divided by 9. So this will be the sum of n terms of the given sequence. So as I said, you can try this by changing this value of 8 to 4, 7, any number, 6, 5, and try. You will get the feel. Exactly the same thing happens, okay, for this type of question. Okay, let's go to the next question, number 19. Please have a feel of that question. Please read that question. You need to feel the question. 19. Find the sum of the products. See, understanding the question is very, very important for all of us. Find the sum of the products. Find the sum of the products of the corresponding terms of the given sequence. There are two sequences. The sequences are, there are two sequences that is given, 2, 4, 8, 16, 32. And the other sequence is 128, 32, 8, 2, 1 by 2. Fine. These are the two sequences given. Question is, find the sum of the products of the corresponding terms. Find the sum of the products of the corresponding terms. So you'll find the product and you'll find their sum. That's what the question is trying to tell us. Find the sum of the products of the corresponding terms. So you'll multiply the corresponding terms and get their sum. You might need a formula, or without that also you can do. Doesn't matter because it doesn't say anything. You can do it in your own ways. So let's say product of the corresponding terms. So that's going to be like 2 into 128, 4 into 32, 8 into 8, 16 into 2, 32 into 1 by 2. So that's going to be 2 is a 16, 1 left is 4, 256, 4 is a 8, 4 is a 12, 64, 32, 16. So this is the resulting sequence that we have when we multiply the corresponding terms of the two sequences. Now our job is to find the sum of this resulting sequence. Alright, at least let's see whether it's an AP or not, or a GP or not. Here, because if it's a geometric progression, then it's, of course you can add. Actually, you can just add these terms because the question doesn't state anything, so you can just add, and I think you get the answer. Because, yeah, that's sometimes it's very simple. Because see, now sum will be. Do we really need to use the formulas here? I don't think so. Because, according to me, because as long as we're doing mathematically correct, doesn't matter. If the question doesn't say you have to use that particular formula, use the sum of n terms of a formula. You have to use. Is it given there anywhere? No, absolutely not. Just they are saying find the sum of the products. So if the question is a simple question, then why do you really need to complicate things by using the formulas? Of course, you can try and test for yourself and see. Of course, it's about application of the formula. Yes, we understand that. But anyway, before we talk much, let's see whether we have the solution or not just by adding, because 6, 10, 18, 20, 26, 2 left, 5, 6, 7, 8, 9, 15, 16, 17, 18, 19, 1 left, 2, 3, 4, 496. Bingo, that's 496. So without actually using any formula, if you have just understood the question, done. Who will say that this is wrong? Everything is correct here. You found out the product of the corresponding terms. Question was to find the sum of the product of the corresponding terms. Sum, S-U-M, sum, A-D-D, add, done. Of course, yes, you can use the formula of a geometric progression, add, find the first term, common ratio, use the formula for Sn. Absolutely correct. You can try it that way also. I've just given you the easiest way, because the question says find the sum. I found out the sum for you. I think this will also work. It will work definitely, until unless the question says okay, you have to use the formula for geometric series, sum, this and that. I guess that's all right, isn't it? Fine, right? If you're not happy with this, okay, you can use the formula and find out. Use Sn formula and find out. No problem with that also. But why should we waste time when it can be done in simple ways like this also? So, okay, number 20. Question number 20. Almost the same question again. Show that the products of the corresponding terms of the sequences form a GP. Again, there are two sequences here. Question number 20. The two sequences are A, AR square dot AR power n minus 1. And the other sequence is find AR square dot AR power n minus 1. So again, almost a similar question to that last question, which states, show that the product of the corresponding terms, again, show that the product of the corresponding terms form a GP. Let's find out the product. After that, we will see what we can do. Product of the corresponding terms A AR square dot AR n minus 1 AR n minus 1. Okay, this is the product of the corresponding terms. Okay, now the question is, prove that they form a GP and also find the common ratio. How do we prove that it's a GP? Basically, the easiest way is that each and every successive term, the consecutive term, should have a common ratio. If you can get that, bingo, your job is done. Let's see. Let's try to get this common ratio, that is second term, first term. AR divided by A. So you're left with R. Okay, let's go for the next two terms. That is AQ divided by, a third term divided by the second term. AR square divided by AR into A into R. R square. What is left again? R into R. So I'm very sure that you continue like this, you will have the same common ratio here, that is R into R into R. This is a term, so R into R. So likewise, we see that we have a common ratio. So ultimately, that's it. That's the proof. You don't have to go too far. So since there is a common ratio, since there is a common ratio RR, the product of the corresponding terms, form a GP with common ratio RR. Common ratio is RR. As per the question, this is just a general question. So that's how you will be doing it. What, you expected something very complicated by the look of the question? No, things are very simple. That's why never judge a book by its cover. Read the book, then only you will know how interesting or how boring the book is. Don't just judge a book by its cover. So sometimes the deadliest question the questions we're having the deadliest looks are always the easiest. Okay, na? Most of us, actually what happens, especially with mathematics, we give up before we even try. At least try once. At least try practicing, just work for some time, try. Definitely you will see, one day it will just come to you. And you will see, it's not that difficult, it's quite easy. Anyway, 21. Find four numbers forming a geometric progression in which third term, find four numbers forming a geometric progression. let the four numbers be AR, AR square, AR cube. As I said, only when find the four numbers, the product is given, that time you will use that condition which I gave you in the previous video classes. No? Otherwise, normal conditions will just use this. So find four numbers forming a geometric progression. Okay, let the four numbers be AR, AR square, AR cube. Fine. First, second, third, fourth term. Forming a geometric progression in which the third term is two cases. First case, in which the third term is greater than the first term by how much? 9. That's what the question says. Find four numbers in which the third term is greater than the first term by how much? By 9. Alright, so what do we have here? AR square is equal to A plus 9. So that's AR square minus A equal to 9, or A common. R square minus 1 is equal to 9. We might get something from here because we still haven't used our second condition. So let's see what the second case brings for us. Second case brings for us second term is greater than the fourth term. Second term is greater than the fourth term by 18. Alright, let's see what we have from here. Second term is greater than the fourth term by 18. So that's like AR is equal to AR cube plus 18. So that's like AR minus AR cube is equal to 18. AR1 minus R square is equal to 18. Equation, let's say 2. We might get something out of this. We do not know. Let's see. As the question suggests, second term is greater than the fourth term by 18. That's what we have. AR common, so 1 minus R square. Chalo. Now the question is find four numbers. Okay, that means we have to find the first term and the common ratio, definitely. So I think, yeah, this I will rub off. This is done, this is done, this is done. Now what can we do? How can we do? What can we do? How can we do? How can we find out the value of A and R? Think. Chalo. Dividing equation 2 by 1. Let's see what we have. AR 1 minus R square divided by A R square minus 1, that is 18 by 9. Let's not forget this equation. I'll just write it here because we might just need that. That is A R square minus 1 is equal to 9. I have a habit of forgetting things. So A minus R square minus 1, R square minus 1 equal to 2 by 1, 9 to 18. So R square done. So minus R is equal to 2. So R value, what do we have? We have minus 2. Alright, so the value of R that we get here is minus 2. Chalo. Then we can work that out in equation 1. Now from 1 we have A. R square minus 1 is equal to 9. A value we will try to find out. R square is minus 2 square minus 1 is equal to 9. So that is A. 2 square is 4. Minus 1 equal to 9. A is equal to 9 by 4. Minus 1 is 3. So 3 3s are 9. Alright, so we have our first term. A is 3. Alright then, that's it, done, job done, no problems ahead. So the four numbers are, once again, AR square, AR cube. So A value is 3, AR that is 3 into minus 2, 3 into minus 2 square, 3 into minus 2 cube. So let's simplify this. So that's like 3 minus 6. 2 2s are 4, 3s are 12. So the four formulas are 8 minus 8 into 3 minus 24. So these are the four terms: 3 minus 6, 12 minus 24. These are the four terms which are in AP as per the given question and conditions. Whew. Alright, let's proceed to the next question, 22. If the pth, qth and rth terms of a GP are A, B and C respectively, prove that this term is equal to 1. If the pth, qth and r terms of a GP are A, B and C, remember we have the letters here A, B and C. A is generally associated with the first term, but as per the question here they say that the pth term is A. So let's, as I mentioned earlier in the previous video, when we have letters which might confuse us, we will use other letters for the first term and the common ratio. Remember that, right? So let A be the first term, capital, and R as the common ratio, because I don't want to be confusing with the pth term, because pth term is A. So let's not confuse it with the pth term. Given pth term, that's pth term, AP, no? An, nth term, pth term, so AP, pth term is A. So that will be like A, R, P minus 1 is equal to A. Got that, no? Simple, because general term is like what? An. So that is A r power n minus 1. So we're talking of pth term, that is A r power p minus 1. It's just that A and R we are using different letters here. Other thing that is given to us is qth term is also given. Qth, very cute. Qth term is B. So that's going to be A r q minus 1 is equal to B. And rth term, earth term, that is A r r minus 1 is C. So that's why if we had used common ratio or small r, capital R, then there would have been a lot of confusion. We will avoid those confusions. Now we're supposed to prove that A q minus r into B r minus p Cp minus q is equal to 1. Let's try to solve this, and then we are supposed to solve and find the value to be 1. A. Now A value I can use from the given condition, that is p minus 1. In power q minus r again. B value, B. A r q minus 1. Yeah. A r q minus 1 r minus p, and C A r power r minus 1 p minus q. Alright, all this goes now. Graph. Alright, let's prove, or let's just solve the exponents. A q minus r power p minus 1 q minus r, A r minus p, r power q minus 1 r minus p, A again, p minus q, r power r minus 1 p minus q. Let's simplify this. So A, common exponents. We'll add the exponents here. A r q minus r plus r minus b p plus P minus Q. Similarly, R, I'll just multiply and add because 1, 2, and 3. I'll just multiply and add together. Okay? So R, that's PQ minus PR. We can also do that. Q plus R again plus QR minus PQ minus R plus P. I'll continue down here plus RP or PR minus RQ minus P plus Q. So that's what we have by solving and multiplying the exponents. You can also do that multiplication on your own also. So R, P, Q, Q. What do we have? A power 0. This is like PQ, QR, plus PR minus PR, plus Q minus Q, minus R plus P minus P, R power 0. Anything to the power 0, anything to the power 0 is 1. Don't we have the proof here as 1? Yes, we do. Absolutely do. So it's simply arithmetic only. Just using some properties of geometric progression, yes, but it's about arithmetic. Addition, multiplication, okay. Multiplication also involved, and subtraction. That's it. Alright, so that's it. Shall we continue again with 2 more problems, or you want to wind up here? I think we are all tired, isn't it? It's been more than 1 hour. So, yeah, maybe the other questions will continue in the other part. So, alright then, we'll wind up here for today. Thank you all for joining in, trying to learn. It's been a pleasure trying to teach each and every one of you. So please study well, work hard, my dear students. As I always say, struggle is very interesting in life. Learn from your struggles. So yes, actually I should be thanking all of you because you have given me the opportunity to teach you, use this platform and then teach you. So actually I should be thanking you. So thank you each and every one of you, and study well, work hard. Good night from my side here, those who are live here online. So good night and see you all in the next session of the class. Okay, so thank you so much. Ronson also, thank you. Thank you each and every one. Alright then, good night. Yeah, thank you Maung. Good night Hilal, good night Maung. Thank you all for being here with me. Yeah, good night. Yeah, thank you Sangeeta. Good night Ronson, good night Sinab. So many good nights to wish, isn't it? So, alright. In general, a very good night to all of you. Sleep tight, sleep well. See you again in the next session. Okay, bye bye.